Right. Thank you all for joining us for another remote high energy seminar in this era of pandemic. We are very pleased and honored to have Stephen Reynolds, who is a professor of physics at the North Carolina State University. Professor Reynolds attended public schools in Seattle. He received a bachelor's degree from physics in Harvard in 1971 and master's and doctorate degrees in physics from the University of California, Berkeley in 1973 and 1980, where he specialized in theoretical astrophysics. During this time, he also worked as a professional violinist, performing with the Oakland Symphony, San Francisco Ballet Orchestra, and other Bay Area musical organizations. He did postdoctoral work at the University of Virginia Astronomy Department and at the National Radio Astronomy Observatory. In 1985, he joined the physics department at North Carolina State University, where he was charged with founding a research group in astrophysics. That group, now numbering 10 faculty, is known worldwide for expertise in high energy astrophysics, with a particular focus on supernovae and their remnants. Reynolds was promoted to associate director in 1990 and to professor in 1995. He is an alumni distinguished undergraduate professor and received the 2012 Board of Governors Teaching Award for North Carolina State University. He is also a fellow of the American Physical Society. Thank you for joining us.
Thanks, Peter, and thanks you all for showing up. So this is going to be an attempt to give an hour-long talk in 40 minutes. Just kidding. It's going to be a 40-minute talk in 40 minutes. There's no doubt that shorter is better in this area, especially in the area of Zoom. So I'll begin with the obligatory boilerplate on why we care about supernovae and pulsar-wind nebulae, but move quickly to what this talk is about. All of the work I'll describe involves measuring expansions of these objects with Chandra. I'll go through a number of examples of this. I don't think any of these are really household words beyond the tiny but fractious SNR community, but I think they're all pretty interesting. The pulsar-wind nebula might be the best known, and then there's an object at the end which I hope you will all explain to me when we're done, because I just have no idea. Collaborators. Most of the heavy lifting here has been done by my NC State collaborator, Kajik Borkowski. A couple of undergraduates have helped in recent years, Peter Gwynn and William Miltick. The G1.9 work was shared more broadly, so Brian Williams, my former graduate student, and Rob Petrie all contributed to that, as well as Una Huang and Dave Green back in the day. And of course, somebody pays the bills. All right. I'm mostly interested in the objects that have something to tell us about their origins. The shell supernova remnants, you might hope to learn really basic things about the supernova. What type of supernova was it? The explosion mechanisms are far from well understood at this point for either type 1As or core collapse, at least in detail. Learning what the ejecta made of can help you with those questions. We now know that supernovae are frequently anisotropic. You can learn this by various indirect inferences, observing distant unresolved supernovae, but of course, galactic remnants can be spatially resolved. So you can document the instabilities and then try to figure out whether they were a result of the explosion itself, of the hydrodynamic interaction of the explosion with in the process of early evolution, or interactions with anisotropic media in the surroundings. A subject close to my own heart that's also relevant for the youngest remnants is the presence of non-thermal, presumably shock accelerated X-rays, that is to say, from shock accelerated electrons. It seems to be found in virtually all, perhaps not exactly all, young supernova remnants. And so studying that may tell you about shock acceleration physics in ways we haven't been able to get at it any other way. The pulsar-wind nebulae, we can learn about how they evolve. They're fairly simple at the very beginning, we think. Pulsar injects more or less constant luminosity and relativistic particles and magnetic field, but then that expands. It interacts with the inside of its natal supernova remnant. All of my cases I'll discuss are sufficiently young that the shell is still there. But to make progress on any of this, you need some pretty basic information, which is not always available. The most important thing probably is the age. fewer than half of the remnants that we can document as less than 2,000 years old were observed as naked eye objects. We can't see most of the galaxy with the naked eye in terms of the typical brightness of supernovae. So we are forced to indirect methods. So one simple method is to learn what the shock velocity is. Now, one way to approach this is by thermal modeling of X-ray emission. This is pretty unreliable. In principle, if the plasma were fully temperature equilibrated, so all species had the same temperature, then measuring the electron temperature, which is what you basically deduce from the spectrum, would immediately tell you the shock speed, but we don't find that to be true. In a few cases, it's possible to learn the ion temperature by measuring widths of lines, and we basically always find that the electron temperature is lower than the ion temperature, so you only get a lower limit on the shock velocity in that method. Optical spectroscopy can tell you about shock speeds, but the non-radiative shocks are very faint, and if it's bright, then it's probably radiative, which means it's wildly unrepresentative of the typical composition of a young supernova remnant. If you had independent knowledge, then you can learn about this non-Coulomb heating that seems to be taking place. Electron temperatures aren't as low as they would be if there were no heating. They're not as high as they would be if there were full equilibration. And for the non-thermal particles, the shock speed is the most important parameter in determining the maximum energy to which particles can be accelerated. So in the two typical possible limitations for that maximum energy, finite age or size of the remnant, or synchrotron losses on electrons. In both cases, the observable, which is the photon energy at which the spectrum starts to roll off, depends as a fairly high power of the shock velocity, fourth power for finite age and square for synchrotron losses. For young pulsar-wind nebulae, it's also important to know the age. In this case, you can learn about the pulsar dynamics, perhaps. If you know the age of the pulsar, well, the pulsar is a neutron star cooling is something you can study this way, although non-thermal emission may make that difficult. And pulsar-wind nebulae also are digging themselves a hole in the innermost supernova ejecta, and you can learn about them that way. So the expansion velocity tells you many of those same things. So what Kajik and I started working on a number of years ago is to get at these by directly measuring the expansion. I mean, it sounds crazy in a way until you start doing the numbers. We are talking about remnants that are all sufficiently young that you can expect blast wave speeds of at least 1,000 kilometers per second. So put in a few numbers, 3,000 kilometers per second at 5 kiloparsecs is 2.5 Chandra pixels in 10 years. And that's easy to measure. It's obvious to look at. I'll show you some examples. And as we say in every single proposal, of course, upper limits also tell you something. So if you're unable to measure a limit, and I'll give you a spectacular example of that at the end of the talk, you still learn something. And part of the moral of this is how to use some of the information that's in your entire image. So how do you go about doing this? Well, the simplest sort of brain dead way to do, and this has been done for many years, and I'm guilty of some of it myself, try to find a sharp edge of the object that's perpendicular to the radius, and maybe average, get an average profile of that in 2 epochs and see if you can see how much it's moved. Sometimes that works. Sometimes it's so obvious that it's quite straightforward. You do waste most of the information in the image. Well, the next step is to try to use all the information at the expense of a very strong assumption. If the object is expanding homologously by some factor, you can take images at 2 epochs, smooth one of them to be the model, and then fit it by expanding it or contracting it to match the second epoch, which is just the data. And typically you fit 4 parameters, 2 parameters for the expansion center, then a linear scaling, which is what you're after, and a brightness scaling, which sometimes tells you things you didn't expect. It has the advantage of using all the image data, but as I said, that's usually an oversimplified assumption. Something we've used more often is simply a subset of the previous method for some part of the remnant that you can isolate. The gold standard, if you have the data, is to use what are called flow methods, non-parametric methods that deform one image into another, assuming that the only changes are due to motions. So if you have that kind of data, you can wind up with the output of an entire vector field of all the displacements. One major disadvantage of this method is so far the statisticians have been unable to come up with a method for us of quantifying the uncertainties. So you have to rely on secondary methods to gauge the uncertainties. So I'll show you results from all 4 of these methods. Just to remind you, Chandra points a lot better than 1 pixel, so we can use sub-pixel methods and easily measure fractions of a pixel. Let me start with a famous example that doesn't require sub-pixel kinds of techniques because it was so spectacularly obvious. This object was known since the early 80s, discovered with the early VLA, Green and Gold, 1984, Nature paper. Then it took, for some reason, 3 cycles of Chandra proposals for us to get an opportunity to observe it with Chandra. And lo and behold, it was 16% larger in 2007 than it had been in 1985. Free expansion age, 140 years. Very highly absorbed. That's why we didn't see it sometime in the late 19th century. The spectrum is almost entirely non-thermal. The integrated spectrum is down there at the right. That's what nothing looks like to Chandra. Well, not quite. That's what an SR cut model looks like to Chandra. We were able to measure in just 2 years, went back to Epoch 2 with Chandra 2 years later, and we're able to measure the expansion quite accurately. And with the deceleration that we expect, we are now quoting the best age estimate of this is 100 years. So it would have been a 25th magnitude object because of the 30 magnitudes of visual extinction around the year 1900. Shock speeds now, therefore, of order 14,000 kilometers per second. There are all kinds of important, interesting questions you might ask, a couple of which I will address in our studies. So here's the first 4 frames in our very gradual assemblage of the movie of the evolution of G1.9. The 5th epoch has been obtained. It's not completely reprocessed. It had to be split over 2 observing seasons, unfortunately, because of all these pesky targets of opportunity observations that keep Pat awake at night. But we will have a 5th epoch. And if you start looking at this, you start seeing, first off, there's a lot of variable background X-ray sources, but also I think you can even tell by eye that the expansion is not homologous, and also that structure is appearing. The very different signals to noise result from the very different exposures. The first exposure is 50 kiloseconds. The third exposure is 1 million seconds. So we're settling down to 400 kiloseconds per 4-year exposure. We hope we can maintain that cadence as long as Chandra exists. Well, we used the flow method using that spectacular 1-million-second observation as one end, and you can see, sure enough, there are very strong non-homologous features to this expansion. The arrows, the length of the arrows is the magnitude of the proper motion. The color shows you the deviation from expansion away from the putative explosion center, that red cross in the middle. And you notice at the north there, the velocities are much slower and look very highly non-radial in some cases. Clearly, there's something denser here that the remnant is expanding into. That explains, we think, why the radio is bright there and the X-rays are faint. Presumably, the density is higher, therefore the shocks are slower and unable to accelerate electrons to the energies at which they could emit synchrotron X-rays. But since the density is higher, the lower energy X-rays or lower energy electrons are more plentiful, so the radio is brighter. So we've solved that mystery. There's an enormous amount more that can be learned from all these data that we'll get to once Chandra is dead and we have nothing else to do. Moving on to objects that are perhaps not quite as well known, this is a fairly obscure but synchrotron-dominated remnant discovered relatively recently. The XMM, the hopelessly blurry XMM image you see to the left there, notice that the radio, which is the red superimposed on it, it's very incomplete in terms of outlining the shell. There is thermal X-ray emission in that region, we think that's where the denser matter is and that this is encountering something. But the rest of the rim is completely synchrotron dominated. So except for those small regions, the spectrum is that of a featureless power law. Well, it was not at all known what the age of this could be until we measured the expansion. Here is the our 2017 image. It's quite faint. There's a fairly bright region in the southwest here, which is blown up to the right. So these are simply grabbed from our paper where we tried to squeeze it into an APJ letter and a little condensed, but the two epochs are shown in pairs at different places. And if you have leisure, you can look at them and really confirm to your eyeball that yes, it is expanded. We got speeds of up to 9,000 kilometers per second in the northwest here, where it's relatively faint, but it's possible to measure that motion of that rim. That makes the second fastest blast wave speeds of any galactic supernova remnant. Cas-A has some features with higher speeds, but not the main shock. Notice down here in the southwest, we've labeled 5 regions A through E. One thing we learned in looking in detail at what the measurements here, now on this plot, the horizontal axis is the distance from the compact central object, which I didn't say anything about. I'll go back there. This thing right here is presumably a non-pulsing neutron star. So this is a core collapse remnant. And the vertical axis here is the expansion rate. So that stuff in the southwest is on average slower, but notice the slowest piece of that 5 region array is the middle one, whereas the fastest are the 2 outer ones. It's wrapping around some unseen obstacle. It is very likely that this will change on a timescale short enough for subsequent Chandra observations to detect it. So also, it turns out this central compact object is the second youngest one that we know of. So that may be useful to folks who are interested in neutron star cooling. A couple other examples of core collapse remnants that are wildly asymmetric. The 2 images on the left are from this thing, MSH 15-52 to the Australian radio astronomers, RCW 89 to the optical people, G320.4 -1.2 to Dave Green. The part we'll focus on is the X-ray brightest part, which is the interaction, we think, of the ejecta from the supernova with this H2 region, RCW 89. So the image from the left is from the New Star paper, but the one in the middle is our observation, smooth somewhat. And this is clearly an extremely asymmetric object. We have a pulsar spin down age, which could conceivably, in this case, really be the age of the object of about 1700 years. The other one we're going to pair with it is G350.1 -0.3, very poorly known object, extremely asymmetric. Lower right shows you a very bright horseshoe-like region. Here is also a compact central object, and this has been saturated in the bright regions to show you a lot of faint other stuff. They're strong hardness gradients immediately obvious in the image. The upper image then shows you a different stretch on that horseshoe to show you that there's strong spectral variations in that as well. So here's a little 3-frame movie through the courtesy of Peter Edmonds. Peter seemed to be on the call. Thank you, Peter. This is outstanding work from the Chandra Press Office. This paper appeared just last fall. And if you just focus on one of these boxes, you can see all sorts of interesting things. And just a few of them is what we documented in our publication. So here we have shown all of the expansions in which we distinguish the component of velocity away from that pulsar in cyan, and the magenta is the actual proper motion. So the motions are pretty radial, but there are some strong deviations. We find that for a distance of 5.2 kiloparsecs, speeds of up to 5,000 kilometers per second are measured. And since we know the real age, we can then measure the decelerations. VT over R, so a deceleration of 1 means undecelerated. And there are some knots there which are very strongly decelerated. And they're lighting up presumably because these are ejectonauts, which are now bashing into higher density material. We can learn a little bit more about that material from spectroscopy. This region up in the upper left in the ellipse, I don't know if you can see my cursor that says SS, is from the slow shock. That's the magenta spectrum here, which has rather different properties close to cosmic abundances, whereas other knots, a couple of examples shown in the spectrum in the lower right, have very strongly enhanced metals and are clearly ejecta. The almost impossible to see blue rectangle outlines what we have identified as the blast wave. Its spectrum is completely non-thermal and is, we think, just another example of electron acceleration to tens to hundreds of TeV energy in a young remnant. We see knots turning on and off in timescales of order 10 years. That allows you to constrain densities because we can fit the thermal spectra for the ionization timescale, divide by that 10 years and get densities of thousands. We think these are the descendants of the kinds of knots that we see at a much earlier age in Cas-A. And the study of them and their dynamics and their composition may give us important clues to the nature of some very asymmetric core collapse supernovae. Here's the same kind of data for G350. Once again, cyan arrows point back to the CCO, and here you see another interaction with an unseen obstacle. The proper motions deviate from radial around it in opposite senses. The stuff in this, the eastern edge of that horseshoe are moving the fastest. And here we had no idea what the age was. We're finding 5,000 kilometers per second proper motions. In this case, the velocities are sufficiently large. There's enough of a radial component that we can measure the Doppler shift with Chandra. And we find space velocities of up to 6,000 kilometers per second. These ejecta are quite iron rich, not exactly what you would expect for a core collapsed remnant, but that's the way it turns out. The image at the bottom shows the whole remnant, and there are some very non-radial motions in features down to the south. This thing up in the north-northeast seems to be the closest that we can find to interaction with more or less solar abundance circumstellar material, and those statements are all documented in the spectrum. Turning now to pulsar-wind nebulae. Here is a combination object which shows part of a shell and a very nice pulsar-wind nebula. A number of you on the call, if you haven't hung up yet, have worked on this object. The pulsar in the pulsar-wind nebula has one of the highest magnetic fields of a rotation-powered pulsar, 510 to the 13th Gauss, and a measured breaking index, which interestingly enough changed after a burst of X-ray in 2006, characterized as being more or less like magnetars. So this object is described as perhaps a bridge between standard rotation-powered pulsars and magnetars. So quite interesting for that reason. So in this case, we would like to know the age. It's clearly very young. Simplistic modeling, I say simplistic because I'm responsible for the physics behind Yossi's very elegant implementation of a one-zone zero-dimensional model, give you an idea that it ought to be only a few hundred years old. Well, we can measure that. In this case, we measured the expansion not of the shell, but of the pulsar-wind nebula itself. I don't think the purple contour is going to be very visible, but that's where we were able to measure it. We had 4 epochs at hand, varying quite differently in exposure time. We aligned on the pulsar. If you're studying the pulsar-wind nebula, you don't really care if the pulsar itself is moving because it's carrying the PWN with it. The 2006 observation turned out to be hampered by a time variable X-ray dust scattering halo, which had to be removed. Well, we did that. And we're able to get quite a nice expansion measurement and an expansion age of 400 years. Unlike shell remnants, which are presumably decelerating, so their expansion age is an upper limit to the true age because they were expanding faster in the past and could get to their current size even quicker. For pulsar-wind nebulae with pulsar injecting constant energy, the expansion is expected to pick up speed. So in that case, the age you measure is a lower limit, but the presumably still correct, very simple modeling of that dynamics gives you radius expanding as time to the 6/5. So if you apply that, you find that this thing is about 500 years old. That makes it the youngest known pulsar-wind nebula in the galaxy, and therefore the youngest known galactic pulsar. So that's good information to know. Now you can start doing detailed analysis of the pulsar to try to understand things. We discovered something. This is the first of the advertised incomprehensible results we have. I'd be happy for any suggestions at the end. The large-scale brightness changes in the pulsar-wind nebula. The upper plot on the right shows you the integrated flux from the whole nebula. It's the 4 epochs. The green line is simply the first epoch flux. In 2006, it was much brighter because of that halo. Our blind correction happened fortuitously to lower the true flux down to exactly the same level as 2006, which clearly isn't right, but within a relatively small error, it does seem to be unchanged. But by 2009, it began to drop. And in 2016, it was really quite significantly fainter. The whole pulsar-wind nebula dropped by 17%. This was confirmed in 2 totally different ways, both by from accounts analysis of the images and also by spectral fits. So we really believe it. The northern part outlined this here dropped by 20% since 2000, and this little bright region in the north dropped by 30%. Just to put this in perspective, the Chandra calibration uncertainties are thought to be of order 3%. So these are all highly significant changes, during which time, by the way, the pulsar luminosity did not change. It's quite strange. Its breaking index and therefore the spin down time scale both changed, but not the luminosity. The profile of the jet emission shows you that the south end, which is on the left side, hardly changed at all in the 4 epochs, where there's a clear drop in the northern end. We are measuring the current pulsar-wind nebula velocity in our expansion rate, about 1,000 kilometers per second. Then if you apply these one-zone models, you can learn what the current density is of the material to which with which the pulsar-wind nebula is interacting. It's about 1 per cubic centimeter, which means it hasn't swept up very much mass, because that's not very big, a few hundredths of a solar mass. So you're driven to 2 possible explanations. Yossi favored a picture in which it was just a low energy supernova. We proposed that perhaps the pulsar-wind nebula is expanding in a nickel bubble. That's a feature that you might expect if the radioactive nickel produced by the supernova is not uniformly mixed in the ejecta, but localized. Then as it deposits its heat due to radioactive decay, it inflates a particular low density region and sweeps up the other ejecta into a shell around that region. So if the pulsar-wind nebula is still expanding into such a bubble, that density that it's currently encountering is not characteristic of the ejecta, and perhaps you could explain this with a less normal core collapse supernova. But this problem with the large-scale flux change is really quite difficult. First one is you can say, all right, what's the basic time scale for large-scale flux changes? It's the sound crossing time scale, where the sound speed is relativistic. So that's short enough. But the pulsar isn't changing. And in any case, that would most easily explain a brightening. How can you make it fade? There you seem to have only 2 possibilities: a dynamical time scale, which is comparable to the age of the object. If you take 1/2 step further and apply our simple model, you get a power law decline of time to the minus 2.2 in the loss-dominated part of the spectrum. That's not nearly fast enough to explain anything. The radiative loss time scale would require you to increase the magnetic field, which would make the part of the spectrum below the turnover even brighter. Furthermore, how do you make this happen through a large region in a short period of time? So we have no idea what's going on here. Somehow, I think it's the conclusion that it's fading is really incontrovertible, but it's absolutely impossible for me to understand at the moment what's going on. But this leads us to the strangest of all the objects. This pulsar-wind nebula was, I think the pulsar-wind nebula was discovered with Swift. At any rate, this spectacular ring around it was found by Swift. This pulsar is fairly luminous and quite fast period, so presumably it's a young object. But the nature of this shell has really been problematic. Its spectrum is totally non-thermal. On the plot here, you see the largest component of a strawman thermal model that we were able to fit under the non-thermal model and not violate the data. So we extracted from that an upper limit on a possible density of any thermal material. So we tried to go through some questions. First, we measured we tried to measure the expansion of the shell, and we got minus 0.04% per year, nominally a contraction. Fortunately, the 90% confidence limits do include zero, but the 90% maximum is only 0.04% per year, means less than 1,000 kilometers per second velocity, or an age of greater than 2,500 years. So this is very puzzling. Our first attempt was to see what kind of a set-off blast wave it could have to be. Well, the thermal limits on the density turn out to require an extremely low mass and an extremely low energy. So this is absurd for any supernova that I know of. It's not a kilonova like neutron star mergers, but it's not even quite a milli supernova. So that seems crazy. Well, another possibility that's attractive until you start thinking about it in more detail is the possibility that this is not the blast wave, but a reverse shock. Now you have no problem in explaining why it might not be expanding very fast or even moving back toward the center. But then that means that this happens when the forward blast wave has swept up an amount of mass comparable to or slightly larger than the ejecta mass. And you know there's not very much mass in thermal material. So the ejecta mass would have to be very small. Furthermore, none of that material out there is evident at all. There's just no emission outside this ring. So the blast wave would have to be completely invisible and all of its shock material invisible. Furthermore, we see this structure in non-thermal X-rays. So this would be a reverse shock, which put all of its energy into accelerating electrons. Reverse shock acceleration to non-thermal X-ray emitting energies is not clearly evident in any supernova remnant that I know of. So this would be a first for that. Now, the advantage you could then make the object very young. Craziest is just to throw up your hands and say, maybe somehow the pulsar-wind nebula is bleeding particles into some pre-existing magnetic structure that lights it up, or something like this. This is three beers speculation, I think. Just for fun, you notice that the pulsar-wind nebula itself is showing significant changes over a few years. So I really have no idea what this thing is, and our only hope, I think, is to try to get a better measure of any possible motion of that shell. Last refuge, back to Chandra, observe it for longer, and maybe we can find out. So here is...
we have an early question here from Pepe.
Sure.
Sorry. Hi. I was wondering, for this object and also the one you showed before when there was a change in the proper motion, you said there is some unseen stuff in there. Has anyone looked at these objects with ALMA?
No, as far as I know.
If you have lots of cold, unseen material, that could change your picture. And
it would be very nice to get some attempt to see molecular material, cold material in the vicinity of any of these objects. None of them are covered by any of the surveys. So we look to see what had already been done. But no, these are great targets for things like that, because you know exactly where to look, and you better see something that's substantial. So go for it. That'd be great. Any other questions or comments at this point?
Oh, since we've got a gap, you'd asked for a 35-minute warning. We're not quite there yet, but getting there.
Yeah, good. Because I'm almost done. So here is a list of all of the remnants that I could find in the literature that have been proposed on any kind of reasonable evidence to be less than a couple thousand years old. So there are various types. Type 1As are slightly overrepresented, but small number of statistics. A hand has been raised. Yes, Pepe.
No, sorry. I'm trying to unraise my hand. And
Oh,
this
you
thing that...
re-raised it.
Don't do anything. I'll lower it.
All
Yeah,
right.
okay. Okay, just to brag a little bit, the objects in blue are the ones that we have measured. This is really a very productive technique if you can find objects that are likely to be this young. I think probably all of them have proper motion measurements now with Chandra, but in the other cases, we already knew the age. So this is really a productive way to learn this information. Now, my talk has been more about learning information that's helpful in subsequent studies than it is about what you can learn once you know the age. But that, again, that's for what we do during the X-ray dark ages when before Lynx is flying and allows us to have comparable spatial resolution in the future. So just summarizing quickly, these four classes of object, G330 is interesting as a very, very fast shocks, just now apparently encountering denser regions. It seems to be expanding in a bubble. Possible changes on timescales of years can be measurable. For those two very asymmetric remnants, G350 and RCW89, the fact that much of the ejecta seems to be concentrated in knots and various small scale structures seems to be an important clue about core collapse supernovae. It was thought for a while that for G350, the explosion center was halfway between the compact object and the bright horseshoe and that it was flying apart, but we've been able to rule that out. The compact object seems to have fewer than a few hundred kilometers per second motion, and that means that presumably there's a lot of unseen stuff on the other side. So these are all peculiar objects where the future is in trying to understand what the X-rays tell us about asymmetric core collapse remnants. And then this G310, well, who knows? It's a bizarre object. We certainly hope to get another round of Chandra on it before Chandra dies and before Lynx flies. So use it while you can. Thanks for your attention.
All right. Thank you, Professor Reynolds, for a really wonderful talk. And now we will open up to questions. If anybody has any questions to ask, please either raise your hand and we can you can speak it out, or if you want to put it in the chat window, I'll read it for you.
I'll go ahead and leave the slides up in case it's relevant for questions. Should there be any questions?
John?
One of the big uncertainties, of course, if you measure the proper motion, is what the distance is. How well are the distances known to these objects?
Excellent question. Not so great. In fact, in one of the more historic examples of superluminal motion, KES 75 moved from 19 kiloparsecs to 5 in the space of about 10 years. So this is, we have to go back to the radio astronomers, improve your H1 models of the galaxy. We would like to have better distances. I don't think, the great thing about expansion ages is of course, is they're distance independent. If you turn them into shock velocities, then yes, you do have substantial uncertainties.
Federico?
Yeah, thanks for the exciting talk. So one question, can you explain a little bit better with more details the flow method? What is the assumption about the uniformity of the velocity in terms of how it's affected by the inhomogeneities upstream of the shock?
Well, okay, let me go back and show the best example of, oh, I see, that's because it's so big a file. That's the problem. Yeah, so this G1.9 image, we used actually I'm not sure it's commercial software, but it's a black box using a statistical method called the Demons method, which is borrowed from the medical community. This was originally developed to study the evolution of tumors as they grow in people's bodies. So a flow method is a generic term for various ways of simply comparing one image to another in units of small structures, and they differ in detail statistically. I'm not sure what else you asked, but that's all I can tell you about what the inside of the method is. Is that what you're asking?
So can you tell, for example, can you tell anything about the density of the material in case?
Oh, I see.
For example.
Not without modeling. The velocities are about 5 times slower in that region now than they had been. But no, one would love to turn this into somewhat more quantitative. I think the way to do that is with hydrodynamic modeling. Once again, this is a job for my retirement, which has begun, but I haven't got to it, of running a 3D simulation into a strongly asymmetric surrounding medium and trying to find out what it takes to produce this kind of deceleration by now. You know, the fact that clearly it hasn't been 5 times slower than the rest of the remnant since the explosion, because it's not that much closer in than the bright limbs. So presumably fairly recently it's encountered something, and I suspect there's a very strong degeneracy between how dense the stuff is and how long it started interacting with it. But to try to turn this into more quantitative information is going to take hydromodeling.
Do you plan to apply also to Casey?
Sorry?
Do you plan to apply also to Casey?
Casey has been pretty well studied, and so we've stayed away from it for that reason. And I'm not sure we could do much better. It's so bright that all sorts of techniques can be used, and thousands of knots have been measured in both optical and X-ray. So I think we couldn't bring that much new to it.
Thanks.
Randall?
Don't necessarily think I have a particularly insightful question here, but the remnant you had with the possibly shrinking sphere or shell, push on a little bit further near the end here. That one, yes, 310. It's just reminiscent of G21.5 in its, Clarion in the center, and then there's this ring. Is there, so this entire ring is, I mean, it also looks like a halo, that it had with a shot, although obviously it's not. And so I'm just wondering if and the last thought I had looking at this was just that in some sense, the crab is another example of a PW, a pulsar with no sign whatsoever of the outgoing shock wave, or at least, not much of a sign. So, we know that it can happen.
Right. The G21.5 can, there you have enough information, you can measure the spectrum of some of that outer shell emission and characterize it, and it makes sense. A large part of the problem here is quantitative. Well, the one qualitative feature that's unusual is that it's so close to the pulsar-wind nebula. That turns out to be hard, not impossible, but hard to arrange. But the problem is that the thermal emission is so faint, if it exists at all, that it forces you into this horrible quantitative corner of such a low energy and low mass event. I mean, if I were allowed to assign any densities, I could make something that looked like this with a reasonable supernova, but it would not be a synchrotron dominated shell. So there is a scattering halo, by the way. You can kind of see it in the lower smoothed image because the pulsar-wind nebula is quite bright, and that gummed up the measurement a little bit. Probably not enough to change the qualitative result. And I was trying to think, is there any possible way this could be some kind of weird scattering effect, some, ice crystals in interstellar space, like a, like rings around the moon, or something? Just some way you could make this be fake? The spectral index is a bit steeper than the pulsar-wind nebula. It's just what you would expect from shock accelerated electrons in other X-ray synchrotron dominated remnants. So it's not that unusual, but I don't know.
Yeah, I was trying to think of some halo way and I couldn't come up with anything either. Is there, yeah. If you got observations with CRISM and you actually measured, say you detected some X-ray, some thermal emission lines, would that, so that you didn't just have an upper limit, would that be a big help?
Oh, absolutely. If you could confidently actually detect rather than simply constrain thermal emission, then at least you know what you're standing on. The absence of strong lines drives you to very short ionization timescales or absurdly low metallicities. But there's really, the constraints are quite poor. You would really, if you could actually detect any kind of thermal emission, it'd be enormously helpful. So for instance, in G1.9, it turned out in a few regions you could see thermal emission, and that's been extremely important. It turns out that there's shocked iron at large radii inside. There's shocked silicon inside the shocked iron in tiny regions. So if we could isolate regions that had thermal emission, yeah, CRISM because of the spectral resolution, but this is really faint too, and it's also rather small. I forget the angular size. It's like 2.5 arc minutes or something, 3 arc minutes. So what's a CRISM pixel?
A little bit bigger than an arc minute.
Yeah, I think you're just going to have real dynamic range problems because the pulsar-wind nebula is so bright. But no, it's absolutely, start writing your proposals.
All right, do we have any more questions? We've certainly got time. All right, if not, let's thank our speaker again for a wonderful talk.
However, it's possible to do that. Well, I appreciate the audience and thanks for tuning in and the good questions. Appreciate it. Thanks for the invitation. Thanks for the pizza.
And see you all next week.